Welcome to the Deep Dive. Today, we're tackling one of the really big questions in AI right now. Can large language models, LLMs, truly understand complex math? Or are they just, incredibly sophisticated pattern matchers? We've all seen these amazing results, right? LLMs scoring incredibly well on things like Olympiad math problems. Genuinely impressive stuff. But what happens when you push them like really outside their comfort zone? Ask them to think creatively. That's what we're getting into today. We're going deep on a really fascinating research paper. It's called Omega. Can LLMs reason outside the box in math? And it's not just about showing off what LLMs can do. It's actually looking hard at their limits, especially when problems need, genuine creativity, new ways of thinking.
Exactly. And Omega, that stands for Out of Distribution Math Problems Evaluation with 3 Generalization Axes, is designed precisely for that. The researchers set up this new benchmark. It's meant to systematically test how LLMs generalize mathematically, going way beyond just memorizing things. So our mission today is to unpack what they found, figure out where the current boundaries are for AI in math, and maybe what that suggests about AI's future overall.
Okay, let's dig into this Omega benchmark then. Sounds pretty clever how they've broken down mathematical reasoning. You said 3 types of generalization.
That's right, 3 distinct axes. And it's actually inspired by Margaret Bowden's work on human creativity, which is quite neat. This framework helps us nail down exactly where these models do well, and maybe more importantly, where they really struggle.
All right, so what's the first axis?
The first one is exploratory generalization. Think of this as testing robustness. Can the model take a problem-solving skill it already knows and apply it to a harder version of the same kind of problem? So the paper uses this example. They train a model to count rectangles inside a regular octagon. Okay. Then, to test it, they give it a regular dodecagon, more sides, more complex. It's the same fundamental skill, geometric counting, just scaled up significantly. It has to stretch its existing knowledge.
Okay, so pushing the known limits. Got it. But what if a problem needs different skills once learned separately to be brought together? Is that the next one?
Spot on. That's compositional generalization. This is where it gets trickier. It requires the model to combine distinct reasoning skills it learned in isolation, to tackle new kinds of problems. Problems that need those skills integrated in novel ways, not just one after the other, but working together. Like, imagine knowing how to find the greatest common divisor and also how to factorize a polynomial. A compositional problem might need you to use both of those skills, maybe in a way you haven't seen before, to find the solution.
Right, like knowing individual musical instruments really well, but then having to play a brand new duet. Yeah. That requires integrating those skills.
Exactly that. It's about building something new from existing parts.
Okay, so exploratory is scaling up, compositional is combining skills. Mm-hmm. What's the third then? You said it was the toughest.
Yes, transformative generalization. This is the real outside-the-box challenge. This demands that the LLM adopts a genuinely novel, often quite unconventional strategy. It has to move beyond the familiar ways of solving things. It's about making that leap, a jump out of the box, as the paper puts it. For example, maybe shifting from a straightforward brute force counting method to a much cleverer subtractive counting approach. Or in polynomial root finding, instead of standard factorization, maybe exploiting symmetry with a smart substitution like x equals t plus at. That totally changes how you tackle the problem. It's not just applying a skill, it's inventing a new tack.
Wow, okay. That definitely sounds like a higher bar. So we have these 3 axes: exploratory, compositional, transformative. What happened when the researchers actually tested the big models like DeepSeek, Claude 3.7 Sonnet, OpenAI's models against these challenges? Do they hold up?
Well, this is where it gets really interesting. They found a sharp performance degradation. Basically, as the problems got more complex along these axes, the model's performance often just tanked. Sometimes dropping to near zero accuracy, even with a lot of computational power thrown at it.
Near zero, even the top model.
Even the top models. And the why is fascinating. They looked closely at the model's chain of thought reasoning. One really surprising thing was that models often find the correct solution quite early in their process.
Oh, okay, so they get it right initially.
Yeah, but then they spend a huge amount of effort, like thousands of extra tokens, just double-checking, verifying, sometimes going in circles. This overthinking can actually make them less stable, and they sometimes end up abandoning the correct answer they found earlier.
Wait, seriously? They find the right answer and then basically talk themselves out of it? That's counterintuitive.
It really is. And there's more. They often fall into these error spirals.
Error spirals?
Yeah, where one small mistake early on leads to another. And because they're autoregressive building on previous steps, the errors just compound. They get stuck going down the wrong path. And another kicker. Sometimes the poor performance on really complex stuff wasn't just calculation errors, it seemed to stem from the models being, well, reluctant to do tedious computations.
Reluctant, like the AI just couldn't be bothered with the hard math grind.
It sounds almost human, doesn't it? But the data suggested something like that. In one problem type, matrix rank, as it got harder, the model spent way less of their thinking process, their tokens, on actual calculation. Below 40%, down from like 65%. Instead, they spent more time on just guessing, making conjectures. But here's the twist. When they did do the calculations step by step, their accuracy on those steps was actually pretty high.
So they could do the math, they just chose not to,
Yeah.
opting for guesswork when it got complicated.
It implies something like a strategic preference for guessing over systematic, potentially tedious calculation at higher complexity. It really makes you think about what reasoning means for these models.
Absolutely. That's a critical point. It's not just that they fail, but how they fail tells us so much. Okay, so if they're struggling with complexity, does throwing more compute power at inference time help? Like generating more possible answers, say 32 instead of just one.
It does help, yeah, but only up to a point, especially at moderate complexity levels. But the gains tend to plateau at the higher complexity levels. And for some problems, like these combinatory letter distribution tasks, performance still hits 0 at a certain threshold, like level 6 difficulty. And crucially, this wasn't because the problems were too big for their context windows. They checked that. A level 6 problem might need, say, under 30,000 tokens. Models like GPT-03 Mini can handle 200,000. So, plenty of space.
So there's not just memory limits.
No. It suggests there might be a more fundamental limitation in how these transformer models handle combinatorial explosion, how they synthesize information when things get really complex. It's not just about giving them more scratch paper. The way they think seems to hit a wall.
Right. Okay, so scaling compute isn't the magic answer. What about reinforcement learning? RL is often touted as a way to make models smarter, more adaptable. Did RL fine-tuning help here? They tested a model called Quen 2.57b Instruct, right?
Yes, they did. And the RL results were, well, mixed. Interesting, definitely. For exploratory generalizations, scaling up known skills, RL actually gave a consistent boost. It helped the model perform better on medium complexity problems, like going from level 1 or 2 up to level 3 within domains it was trained on. For instance, in a logic puzzle domain called zebra logic, RL pushed the accuracy up by over 50 percentage points on problems slightly outside the training distribution. So a clear win there for making models more robust within familiar territory.
Okay, so RL helps them stretch existing skills further. That makes sense. What about combining skills? Compositional generalization.
Here's where it gets complicated. RL did significantly improve performance on the individual isolated skills. The model got much better at, say, polygon rotation on its own or pattern matching on its own. But, and this is the key thing, those improvements on the individual pieces did not reliably transfer to the problems that required combining those pieces. Models that mastered the parts often failed when the solution needed to integrate them. The paper gives an example combining GCD and polynomial roots again, where RL tuning resulted in basically 0 improvement on the combined task, even though it improved the individual skills.
Wow, that's huge. So they learn the ingredients, but not the recipe for putting them together in a new way.
That's a great way to put it. It really points to a deeper issue about synthesis and integration, not just component mastery.
And what about the really creative stuff? Transformative generalization. Did RL help models think outside the box?
Unfortunately, no. This seems to be where current methods, including RL, really hit a wall. RL helped a lot on familiar problems within the training domain, where the known strategies worked. But on the out-of-distribution transformative problems, the ones requiring genuinely new approaches performance stayed stubbornly near 0, often literally 0%. RL just didn't seem to push the models towards discovering truly novel reasoning patterns.
0%, even after RL fine-tuning specifically designed to improve reasoning.
Exactly. And even worse, in one specific case, they highlighted the matrix rank problem again. RL training actually seemed to hurt performance on the transformative tasks. It caused a 30 percentage point drop.
A drop? How is that even possible? Optimizing it made it worse at the hard stuff.
It's pretty startling, isn't it? The thinking is that the RL process might have inadvertently reinforced brittle heuristic strategies that worked well on the training data, but actually made the model less likely to explore or find the more elegant, transformative solutions needed for the harder road problems. It optimized for the known path, potentially blocking discovery of new ones.
That's a really sobering finding. It suggests optimizing for current benchmarks might even hinder progress towards more genuine intelligence sometimes.
It certainly raises that possibility. It shows the limitations of simply trying to reinforce existing pathways when the goal is true innovation.
So bringing this all together, what does this Omega study tell us about the future? About AI tackling truly complex math or, any really complex problem that needs creative thinking?
I think it underscores a really critical gap we still have. Current LLMs, for all their scaling and benchmark successes, they still fundamentally struggle with what we might call genuine mathematical creativity. They are fantastic at interpolation, applying learned procedures, maybe to slightly harder examples, but they really falter at true innovation, adapting, combining, inventing new strategies when faced with fundamentally novel challenges.
So great students, but not necessarily great inventors yet.
That's one way to look at it, yeah. They haven't quite made the leap from applying knowledge to generating truly new insights or methods, especially under pressure from complexity. And this really frames the challenge ahead. The paper argues we need smarter scaling solutions, not just throwing more data or compute at the problem in the same old ways. Things like just adding more similar data or using simple synthetic helpers might give a short-term boost on benchmarks, but they could actually hide these deeper structural weaknesses in how the models reason.
Right, masking the problem instead of solving it.
Exactly. The real goal isn't just better scores on today's tests, but building models with fundamentally more robust, flexible, and efficient reasoning, models that can genuinely tackle problems they've never encountered before.
And the paper suggests some paths forward, like curriculum scaffolding.
Yes, exactly. Gradually increasing complexity, kind of like how humans learn, and also ideas like meta-reasoning controller systems that could perhaps recognize when the model's standard approach isn't working and trigger a search for alternative strategies.
Building in a kind of self-awareness or strategic flexibility.
Something like that. Moving beyond just computation towards, actual problem-solving strategy.
What a journey. We started seeing these LLMs as math whizzes, but this deep dive into Omega reveals these really profound challenges still ahead. They're incredible at applying what they know, even scaling it up. But that true spark of creativity, combining ideas in new ways, inventing new approaches, that seems to be the next major frontier.
Absolutely. And the Omega benchmark itself is a valuable contribution. It gives us a framework, a tool to measure progress beyond just accuracy on known problem types. It helps us understand the how and why of their reasoning or lack thereof.
So for you listening in, this really highlights that while AI is incredibly powerful today, those deeper aspects of human-like intelligence, adaptability, genuine creativity, the ability to truly think outside the box are still very much frontiers under active exploration.
And maybe a final thought to leave you with. Considering these findings, are there complex, real-world problems where we might be relying on AI for the parts it can handle easily, the known parts, while potentially missing or oversimplifying the truly novel outside-the-box aspects that current AI struggles with? What complex systems might need more than just pattern matching? Something to think about.
That's a great question to ponder. Thanks for diving deep with us today. Until next time, keep exploring, keep questioning, and keep learning.